Well, it's a topic I think we can all relate to.
Yeah.
They're all good topics, Jacob, right? But I see your first graphic there talking about wind and the Coriolis force and all these kind of things. It's going to be a good one.
Well, we live in North Dakota, and with our blizzard conditions that you said can just be because of winds, ground blizzards, this is an appropriate topic for this week. So we've gone over what causes the wind before, but we'll give a quick refresher here and then talk about why wind flows counterclockwise around storm systems, areas of low pressure, and clockwise around areas of high pressure. So air pressure is always trying to reach a state of equilibrium or balance, flowing from areas of high pressure to low pressure. So if we have a weak area of high pressure and a weak area of low pressure, we'll have relatively weak winds with small changes in pressure between those two centers. Whereas if we have a strong area of high pressure and a strong low pressure, the winds will be much stronger, larger change in pressure, and what these lines are, these are called isobars. Those will be important as we go over the next couple of minutes. Lines of equal pressure, those are packed closer together. So you probably heard us talk about a tighter pressure gradient. Once we have those lines of equal pressure packed a lot closer to each other, tighter pressure gradient, that equals stronger winds between our areas of high pressure and low pressure. Now, the pressure gradient force, or the PGF, is just that horizontal pressure difference. It sets the air in motion, making our wind from high pressure to low pressure. So if we only had the pressure gradient force in our atmosphere, winds would blow directly out from areas of high pressure across our isobars, across these lines of equal pressure, and directly in to areas of low pressure, directly across our isobars. But this isn't what happens in the real world. We'll go over why that happens in a second, but this is just with the pressure gradient force. Of course, we live on a rotating Earth, and the speed at which the surface moves at the equator is a lot faster, about 1,000 miles per hour, than the speed that you're rotating at the poles, practically 0 miles per hour. That sets up our Coriolis force that we'll get into in a second. But think about this. If we're rotating that much faster at the equator than the poles, and if we shoot a projectile from the equator towards the poles, we would expect it to go straight towards the north, straight towards the poles. However, the actual path is deflected to the right in the northern hemisphere because our objects remember the initial momentum they had. And when we're launching an object at the equator with a faster speed, that's going to maintain that momentum and veer it to the right. If we're launching that projectile in the northern hemisphere, it's the opposite in the southern hemisphere. But focusing on the northern hemisphere where we live, if we fire that projectile north, it's traveling faster to the east than our intended target is. And that veers that wind, or veers the projectile in this case, to the right, and that's our Coriolis effect. So if there was no rotation of the Earth, the atmospheric circulations would look like this, with warmer air at the equator flowing southward and northward towards the poles. Not very interesting. The atmosphere would only circulate between the Earth's polar regions and the equator. But we know that with our rotating Earth and that Coriolis force that I just talked about, our deflection goes to the right in the northern hemisphere. And this deflection of the global wind pattern sets up our ocean currents as well as those global wind patterns. The Coriolis force is named after a French mathematician. So this Coriolis force acts 90 degrees to the right of motion in the northern hemisphere. You can see that here. So with our pressure gradient force that we talked about earlier, again, just from high pressure to low pressure, but the Coriolis force acts 90 degrees to the right, and the resulting path of the wind is curved like that. So remember that 90 degrees to the right of the actual wind direction. If we have higher pressure down here and lower pressure up here, the start of an air parcel right here with no motion, Coriolis force acting to the right of that. And that's veering it to the right as it goes closer and closer towards the lower pressure. So the path of the wind then ends up parallel with our isobars, these lines of equal pressure. Our wind is going straight across instead of going towards the lower pressure or towards the higher pressure. So in this diagram, low pressure up there, high pressure down here. Coriolis force acting essentially in the opposite direction of our pressure gradient force, leading to our wind direction being parallel with these lines of equal pressure, parallel with these isobars. And that's what we call the geostrophic wind. So it's a balance between the Coriolis force and the pressure gradient force. The winds are then flowing parallel to our isobars. However, that's not, again, what we see in the actual world. We have to add in one more force, and that's friction. Friction is important, especially near Earth's surface. It slows the wind and impacts the direction. So if we're in the upper levels of the atmosphere, that diagram I showed you on the previous slide works perfectly, with the wind flowing directly parallel to our lines of equal pressure, our isobars, with the Coriolis force and the pressure gradient force directly opposite of each other. However, once we're closer to the surface, friction acts opposite of the wind direction and veers our wind a little bit closer towards the pressure gradient force, a little bit closer to the area of low pressure. So therefore, we have the wind crossing these lines of equal pressure at an angle, and it's about 30 degrees. It's less of an angle over the oceans where there's less friction, more of an angle over mountains and land where there's more friction for the air to encounter. So high pressure, low pressure. Pressure gradient force wants our wind to go this way. Coriolis force wants our wind to go this way. Friction wants it to go this way. The resulting wind this way. So all of these forces combined. Resulting wind goes this way across our isobars, across our lines of equal pressure, a little bit towards our area of low pressure, and that's how we get rotation to form, these larger scale rotating winds around areas of low pressure and high pressure. So around an area of low pressure, we have winds blowing inward, counterclockwise flow. Around an area of high pressure at the surface, winds blowing outward, clockwise flow, and that sets up vertical motion. With winds blowing clockwise and out of an area of high pressure, we have sinking, descending air, generally calmer weather. With winds blowing counterclockwise and out from inwards towards an area of low pressure, all that wind converging towards one point, it has to go up in the atmosphere. That leads to vertical motion. And with areas of low pressure, we oftentimes see storminess, clouds, precipitation, etc. So let's look at a weather map that's happening right now. This is our strong system that's delivering blizzard conditions to especially eastern North Dakota. I plotted these isobars, these lines of equal pressure, as well as our winds. And notice how they're crossing those isobars at a little bit of an angle towards the areas of low pressure and swirling around that center of low pressure in a counterclockwise motion. A little bit farther to the west, an area of high pressure. Winds are relatively calm right under that area of high pressure, flowing outwards around it in a little bit of a clockwise motion. A couple other examples around the world right now, and over the Atlantic Ocean, you can see these winds coming out of the area of high pressure in a clockwise motion and crossing those isobars at a little bit of an angle because there's a little bit of friction still over the oceans, so it's not following those isobars directly parallel. Again, over in the Gulf of Alaska, area of low pressure, winds going counterclockwise around that, and crossing the isobars at a little bit of an effect. So it's all because of the Coriolis force that sets these winds into motion, causes them to veer a little bit to the right in our northern hemisphere where we live, and causes our winds to be in those counterclockwise motions, sets up storm systems for areas of low pressure.
So I still hate the wind. Thanks.
Yes, you do. But now you know kind of the science behind the wind.